I welcome you all to the current installment of the SLAC Public Lectures. We're very pleased to have today Justin Myles, who will tell us about really the latest news in our study of the structure of the universe. So we're very pleased to have Justin here today. You probably know, and you'll find out a lot more about this in this lecture, that SLAC is a participant in one of the largest surveys of cosmic structure that have ever been carried out. We're partners with other astronomy groups and also other Department of Energy laboratories. The name of the survey is the Dark Energy Survey. You'll hear a lot about it in this lecture. Justin was an undergraduate at Yale and came here to SLAC and Stanford to work with the Kavli Institute group. That's a big part of this Dark Energy Survey collaboration. So he's writing his thesis basically on this data, which is both an exercise in kind of a deep dive into the form of the universe and a big data mining exercise, since the database collected by this survey is truly enormous. So Justin will now tell us about all these things, and I hope you will welcome him. Let me just say one more thing before he begins. You'll see at the bottom of your screen a Q&A box or something to click. If you have questions, please type them into the Q&A box. At the end of the lecture, Justin and the two panelists who are also named on this slide will answer your questions. And hopefully that will also be a part of this event, which is interesting to you. So once again, please, if you have a question, type it into the Q&A box, and you may, I hope, hear it at the end of the lecture. So thank you very much for coming. And Justin, please take it away.
All right. Thank you very much, Michael, and thanks to everyone who's come. I'm very excited to be able to talk to you today about the tug of war that shapes the universe. Without further ado, I'll sort of just get started. But again, just want to encourage people to write in their questions for our group here. We're really excited to be able to talk to you today. All right, so there are three main questions that we'll talk about in today's lecture. The first is, what is modern cosmology? What does that mean as a field of science? And the second is then, how does the Dark Energy Survey, one experiment within modern cosmology, how does it fit into the field of study? And how does it study the universe? I'll talk in depth about how we make measurements with telescopes to understand the basic rules governing the universe. And we'll finalize the talk by talking about what is the state of the art. We'll look at the most recent results and we'll try to understand them. So what is modern cosmology and what do modern cosmologists do? Modern cosmology is a part of astronomy, which is often considered the oldest science in a sense. And it is a part of this field which is differentiated by the sheer amount of data that we can observe today and how that relates to the fundamental rules of physics. So one definition you could be given is that cosmology is the study of the origins, the development, and the future of the universe, as inferred from observations of the night sky. So astronomy, since time immemorial, has been about looking at the sky, and in particular the night sky, to figure out what's going on out there in the world and to figure out our place in the world. Cosmology focuses on how the universe has developed. What is the history of the development of the universe, and what is the account of all the objects that are in the universe and how they interact? So it's very closely related with the fundamental laws of physics. So what is a cosmologist? So I'm very fortunate to be able to work in modern cosmology. I am a PhD student, a graduate student at Stanford University. So I'm working on my PhD. And my day-to-day involves collecting data with telescopes and analyzing them with specialized algorithms. I wanted to give some visual sense for what that looks like in the modern world. So here's an image of me working with the telescope. This is the WIYN telescope on the Tohono O'odham Nation in present-day Arizona. And so modern-day telescopes, the way they work, we don't look through an eyeglass. They're hooked up to advanced cameras. And here you see all the things we might want to interact with while we're collecting observations. So we're tracking objects that we want to look at in the sky as they move because of the Earth's rotation. We're looking at the camera in particular. We're looking at the positions of fiber optic cables that are picking up light from individual galaxies, as well as looking at weather and how the telescope itself, which is a complex machine on its own, how it's operating. So I thought it might be helpful to think about a historical analogy. So human accounts of all the elements of the universe have changed over time. And there are many such accounts in the history of many different cultures. I have here an image of one particular account. This is known as the Ptolemaic model from ancient Greece. And the reason I wanted to pick this is because it has so few objects. It's something that you can sort of wrap your head around. In this picture just depicts one understanding of all the stuff in the universe. There's Earth, there's some of the other planets, and there's an edge. And that was it. And I think this is helpful to think about because it really did explain many of the observations that were possible with the naked eye, right? People could tell that the way the planets moved is not necessarily exactly the same as the way the stars move in the sky. The way that planets look is not exactly the same. So we should always stay grounded when we're thinking about these problems in that they're related to what we see in the sky and trying to explain it. But of course, our understanding has evolved quite a bit over the years, and it's involved in large part due to an increase in what we can see because of improvements in telescopes, and both in their size and their sophistication. So here's an image collected by the Hubble Space Telescope. This is a telescope which is a satellite, and what you're seeing here is a deep image of a tiny patch of the sky called the Hubble Deep Field. So in this image, this looks very different from what you'd see with the naked eye. Each of the specks you see here is a distant galaxy. It's a galaxy apart from our own Milky Way. And you see a huge number of these galaxies and of a wide variety in color, shape, and size, because some of these are closer and further. There's a huge variety of what you're seeing here. Modern cosmology, one large part of modern cosmology is using observations of galaxies like this and huge numbers of these observations in order to understand the basic rules of the universe. So let's talk about the modern cosmological model. So it starts, as many people will know, with a hot Big Bang. So there's a Big Bang. That's the start of this story. And then immediately afterward, the universe is expanding and becoming larger, but it's very hot and smooth. So it's called a primordial soup of all the stuff in the universe. And as the universe expands, it cools. And what plays out in this cooling is that gravity can then, gravity is an attractive force where matter attracts other matter. It can then form structures. It can get clumpier. So that's what's happening as the universe is cooling and expanding, that structures can eventually be allowed to form. So the universe starts out as hot and smooth, and over the course of more than 13 billion years, it becomes colder and clumpier. So if you look at the edges of this diagram, you see in the early universe, there's this hot soup where everything is sort of the same. And it's very different from the present day universe. When we look out, we see regions where there's a lot of matter, like galaxies, and then regions where there's really nothing at all. It's cold and empty, cold voids. So that's the history of how the universe has developed. So you can already see that there's this tension between the expansion of the universe and gravity, gravity tending to form structures by pulling things inward, and expansion of the universe because space itself is stretching, which tends to suppress that formation of structure. There are other parts of this story, of course. There are exploding stars. There's weird things in space which dump energy, in a sense, out into their environments. But on the largest scales, this story is what tends to determine what the universe looks like. So with that basic understanding, now I'm going to talk about what are the problems that we're stuck on, because we think this story is very successful in many ways, but also merits additional scrutiny and verification. So the first thing I want to talk about us being stuck on, what are the nature of dark matter and dark energy? So these are two components, really important components of the universe. The name for the modern cosmological model is lambda CDM. The lambda stands for a particular kind of something that can be interpreted as a dark energy, and the CDM stands for cold dark matter. So these are really important components. Where do they fit in? All right, so this cupcake represents all the stuff in the universe. It's something we call the energy budget. How much of the energy in the universe is a particular thing? The stuff we're familiar with, all the atoms in the universe, everything that's making up the stars and the planets, asteroids, gas, dust, all of that, those are just the sprinkles on this cupcake. The ordinary matter is actually a very small amount of the energy budget of the universe. Most of the matter is actually something we call dark matter. It's called dark matter because it must not interact very strongly with light. It's not easy to see if it does interact with light at all. And when I say that, it can be more than one thing. But in general, we refer to dark matter as at least one thing that we can't see in a normal way. The evidence for dark matter stretches back decades. So there's a huge amount of evidence in favor of the existence of some form or forms of dark matter. One of the more intuitive explanations is that we can measure the speeds of objects in space as they move, and things will orbit around centers of gravity. So for example, the stars in the galaxy will orbit around the center of a galaxy. The galaxies in a cluster of galaxies will orbit around the center of gravity of that system. And when we observe the speeds of those objects as they whip around the center of their system, the speeds are really, really fast. And when you add up all the mass that's holding it in by gravity, it doesn't add up. It's not enough to hold these things in, given how fast they're moving. So there must be some other matter that we can't see to hold everything together. And so that's most of the matter. That accounts for much more of the energy budget than the ordinary matter. And then there's another component, which is actually more mysterious and more recent, at least observationally, which we're calling dark energy. And this is something that we have introduced to our model because the expansion of the universe, it turns out, is accelerating. And we need an explanation. We need some cause for that acceleration. And there are ways to accommodate that in the laws of physics. And because this is something that can be interpreted as a form of energy in the way that it can be introduced in the equations, but it's also something that we don't really see in an ordinary sense. It's called dark energy. So that's actually most of this cupcake. So we need to better understand the nature of dark matter and dark energy. The evidence for the existence of these things is compelling, but we don't have an excellent description of how they operate in the way that we do for all the ordinary matter that we've been working on for much longer. So let's talk a little bit more in detail about this. So dark matter, as I've said, we have quite a bit of evidence for the existence of dark matter, but we don't know what it is in the sense that we know what, for example, electrons are. We can't give an exact description of what it is. And again, it can be more than one thing. So here's a Venn diagram. This is super complicated. There's no need to look at each individual element of this Venn diagram. But this is illustrating all the different theories of dark matter that there are. And we have many experiments here on Earth trying to detect this dark matter, but we still just don't know. So the point is that we want to better understand from all kinds of observations dark matter in order to figure out exactly what it is. And now let's talk about dark energy and the expansion of the universe. So keeping with our theme of baked goods here, now we have raisin bread, okay? So the image in the bottom illustrates raisin bread before and after it's baked. So the left-hand side, you see a lump of dough, and the right-hand side, you see the baked bread. And each of the black dots represents raisins in the raisin bread, or galaxies in the universe, okay? As the dough bakes, as the bread bakes, it expands. And so what you'll notice is the distance between each of the either raisins in the raisin bread, the distance between them increases after you've baked it, right? Every raisin is farther away from every other raisin compared to when it was first baked or when it was not baked. So this is an analogy for the galaxies in the universe. We see something similar playing out when we observe galaxies in the universe. All the galaxies are moving farther away from each other. essentially. So this is how we can measure the expansion rate of the universe, because we can measure the velocities of things in space and the positions of things in space. So this is something that we're stuck on and we're working on understanding. We want to measure this very directly. And it's something that we care a lot about in modern cosmology. So now you should have a better intuition for the title of this talk. There's a tug of war between the gravitational effects of dark matter and dark energy. And this tug of war, it determines how clumpy the universe is. On one hand, we have the inward pull of gravity, where dark matter, being the dominant form of matter, is going to form structures. And on the other hand, we have the stretching of space itself, accelerated by dark energy, which tends to suppress the formation of structures, essentially pull structures apart because space itself is stretching. So we want to measure this very directly. We care about exactly how clumpy the universe is because it tells us how this tug of war is playing out. Right now that's qualitative, but I'll try to give a bit more detail about how we quantitatively talk about clumpiness. But that's the big idea of what dark energy survey is measuring primarily. All right, so let's look at some data about how that looks. So this is an image of different data. It's the Sloan Digital Sky Survey. In this image, every colorful point represents a galaxy, okay? And the center represents where we are. As you get further away from the center, we're looking at galaxies that are further away from us. There are two other directions you can look at. One of those directions we've squashed over, and the other direction is the angle on the circle, so clockwise or counterclockwise in the circle. So what you'll notice is the galaxies are not uniformly distributed. It doesn't look, for example, like those of us who are old enough to know what television static looks like, it doesn't look like that. Instead, you see some parts, there's a lot more galaxies, other parts, there are these cold voids. This is a qualitative description of how clumpy the universe is. By just mapping galaxies in space, we have an understanding of how clumpy the universe is. Now, there's another measurement we can make, which is really interesting. So now we're going back in time to the very early universe, just 300,000 years after the Big Bang. So this is very early universe. And what I'm showing here is the oldest light in the universe. This is the oldest light that's streamed out and can still be observed today. It's really everywhere. The map is an oval because I'm representing an entire sphere in 2D plane. So you're seeing your screen is flat and I want to represent the whole sphere. So in order to do that, we have to distort the sphere in some way. This is just a distortion of that sphere so you can see the whole sphere. We're looking at everywhere in the sky. And this light can't be seen by the human eye, but it can be detected with telescopes and picked up by specialized cameras. So here, what you're looking at, what the color represents in this map, is the temperature of the source of that oldest light. And so you see that there are bluer regions, colder regions, and there are redder regions, which are warmer regions. So you see that even in the early universe, 300,000 years after the Big Bang, it wasn't perfectly uniform in temperature. Now, an important feature here is that the temperature scale is very, very, very tiny. So this temperature scale is showing very tiny differences in temperature. Mostly, it is actually basically the same temperature. But the scale here, the units of this are millionths of a degree. So very tiny differences in temperature, which we have worked over many decades to be able to measure precisely. But you'll notice that this is actually apparently less clumpy than the late universe image we saw. And when we looked at the galaxies, there were some regions which were more obviously not random, whereas this field appears to be a little bit more random. So this brings us to a really important idea. It's that we want a model which explains both of these images. They're very different times in the universe. One is very early in the universe, the other is very late. They're very different kinds of data. One is looking at the oldest light in the universe. The other is looking at, for example, the positions of galaxies, for example. But we want a story that ties together these observations. And this is what we're working on actively doing, tying together all of these observations. And at this point, it's probably worth mentioning that, so our modern cosmological model, as you can now see, it doesn't just explain the observations of the galaxies in the sky. It explains many, many different kinds of observations. So modern cosmology we observe light of all wavelengths, not just what the human eye can see. It's very closely connected to fundamental physics, and we're trying to tell a story which incorporates all of these things. That said, another piece of context is that this interesting story between the nature of dark matter and dark energy and how it affects the structure of the universe, it's an important big question about the universe, but I want to be clear that it's not the only mystery in physics. So it can seem sometimes like this is everything. There are many other mysteries in physics, but this is one big field of inquiry that we're engaged in. All right, so now coming back to our diagram for the history of the universe, we want to be able to observe the oldest light in the universe, called the cosmic microwave background, and then also measure the late universe, the galaxies that we see nearby us, and tell a story that can explain both and explain how you get from one to the other, because we know the clumpiness is changing. So we want to be able to quantitatively describe exactly how much that's happening. So that's the context. That's the big idea that we're trying to investigate. And now I'm going to talk about how we do that in practice. So we're going to switch gears here. So now we're going to be interested in how do we actually collect data to do that, and what are the challenges to collecting those data, of which there are many, and many scientists work for their entire careers on one particular challenge because these are such complicated experiments we want to do. So the experiment I'll be talking about is called the Dark Energy Survey. So let's think about building a cosmological experiment. We need a telescope, and the first thing we need to do is figure out where we want to put it. So here you see an image of where the Dark Energy Survey telescope is put, the Victor and Blanco telescope. So this is in a desert in Chile. It's the driest place in the world. That's because it's situated between these two mountain ranges, which essentially block out moisture from entering. So that's really good because it makes the atmosphere very stable, and that's what we want when we're observing things from space. That also means there'll be less nights covered with clouds, because astronomers still have to deal with cloud cover that ruins data. And in addition, it's far from where lots of people live, so there'll be less light pollution, in fact, affecting our data. And also, we observe at our observatories, in general, astronomers observe light of all wavelengths, which stretches not just what we can see, but stretches to the radio waves, for example. And radio waves interference from human telecommunications interfere as well. So this isolated dry site is really perfect. And one thing, just looking at this image, you'll notice is that, so the dome is closed and there's a window which will open when it's nighttime so that we can observe. And you'll also see that there's these windows essentially in the dome. Those have been opened even though the sun is up, because they want to equilibrate the temperature inside the dome with the outdoor temperature. That's because temperature differences can lead to turbulence, atmospheric turbulence essentially, and you just want everything perfectly still as much as possible. Then you need a big telescope. So we are interested in observing as many galaxies as possible. And that means we want to observe very faint, very distant galaxies. In order to do that, we need to collect as much light as possible. The theme for how to understand how we do that is that to think of the telescopes as buckets for light. If you think of a telescope as a bucket for light in the way that a bucket might collect rainwater, then it becomes clear why you want it to just be bigger. The bigger the telescope, the more light you can collect. So our telescope is 4 meters from end to end in diameter, and this is it's important to collect as much light as possible. The other thing you need is a very big camera and a very advanced camera. So there are important differences between the cameras we use in astronomy and the cameras that you might be familiar with from your day-to-day life. So one is that it's much bigger. So here, for example, you see the dark energy camera, constructed from 2008 to 2011. It has 570 million pixels. So that's what 570 megapixel means. And each of those pixels is 15 microns by 15 microns. Don't expect you to know how small that is, but for comparison, the iPhone 4, which came out in 2010, the pixel sizes were much smaller, 1.75 micron by 1.75 micron. So each of these pixels is large, and there are many, many more, because the iPhone had just 5 million pixels compared to our 570. This camera is 44 centimeters across, that's about 17 inches. And another important difference here is that we're interested in detecting very, very faint light. So the silicon wafers, the chips, in a sense, that we're using to collect those light that you see here, these chips, they're thicker because we want to collect, when a light particle hits it, we want there to be more of a chance for it to interact with the metal and get detected and get converted to an electrical signal that we can pick up. It's also important because we care about very red galaxies, and red light is of lower energy. So we need the thick CCD, or the thick camera chip, excuse me, in order to detect as much of those red light particles as possible. So in the bottom left, you see one image from the dark energy camera, DECAM, and the green, there's a tiny green like point. That's the size of the iPhone 4 camera at the time. So we've talked about a big telescope and big camera. The next thing is a big survey. So remember that we're interested in understanding how clumpy the universe is. So if I gave you observations of 2 galaxies, you'd obviously not be able to say how clumpy the universe is. It just is not the right data. So that gives you a sense that we're interested in a statistical measurement of huge numbers of galaxies. Without huge numbers of galaxies, you can't do the kind of science we're interested in. Any particular galaxy doesn't tell us about the nature of dark matter and dark energy. It's only an ensemble of a huge number of galaxies that can do that. So you want to do a big survey. The dark energy survey is shown here. It's did about an eighth of the sky over 6 years. And within the first 3 years of data alone, we have good measurements of position and shape for over 100 million galaxies. The raw images is over 100 terabytes of data. And one thing to point out here is the shape of this survey, just to give you a sense for how astronomers think and why it looks sort of random, is that we want to be able to combine our data with other telescopes which observe different kinds of light as well, and that gives us more power. So you're seeing a weird shape because we've designed a shape that's going to overlap with other kinds of telescopes, which are maybe not in Chile in the southern hemisphere, but at the very edge in the northern hemisphere, so that's easier to see. And we also want to avoid certain parts of the sky. So for example, the Milky Way plain, there's a lot of stars and dust, and that's going to make it harder for us to see our really faint galaxies that we're particularly interested in. So every little detail here has been designed for a particular kind of science. And this is actually something that's an evolution in astronomy, that we've designed this long-term experiment to specifically achieve one goal, among others. So big telescope, big camera, big survey, big data, that means you need a big collaboration. So the Dark Energy Survey is a project with over 400 scientists working on many things, not just the experiment that I'm describing today, because there are many other things you can do with the data. But this is a kind of project which is doable only with a large team. So we have an international team with many people, including many people right in college and right after college, as well as more senior scientists, all working together to achieve this common goal. So one thing worth knowing is that in order to achieve this goal, it requires people who can engineer good machines and develop innovative things like cameras, as well as work with advancing algorithms for processing and analyzing data, and understanding how those data then relate to the underlying scientific theory that we're trying to understand. So there's a lot of variety in what people in the Dark Energy Survey do. So that gives you a sense for how the Dark Energy Survey operates. Now let's talk about some of the scientific principles it relies on and the kinds of measurements it's trying to do. In order to do that, we need to understand gravitational lensing. So this is something which is predicted by Einstein's theory of gravity. And it says basically that gravity can be thought of as the curvature of space itself, which is due to the presence of energy and matter. So here in this diagram, you see in the distance, there's 3 galaxy shapes. And they're going to the light from those galaxy shapes is going to pass through space to get to us. And along that path, we've put in 2 clumps of dark matter. That's what those 2 circles represent. Those clumps of dark matter will bend space itself. This is a result of the theory of gravity. And because it bends the space itself, that light will be deflected. So the shape that you ultimately observe will be different. So if we just look at each individual shape in the background, then compare it to the shape at the end of the arrow, it's been sheared. The shape has been altered. We want to observe this. So already you can see if the presence of matter changes the shapes of distant galaxies, then measurements of the shapes of galaxies can be used to understand what the distribution of matter that it passed through was. That's one of the key principles that the Dark Energy Survey relies on. So here's an analogy I like to make. So here, sorry, I'm just gonna move out so the text in the bottom on the right says this is not a galaxy cluster. I'll be covering it now. On the left-hand side, there's a painting by René Magritte. It says in French, this is not a pipe, but it's clearly an image of a pipe. The purpose of, or the idea here being that the pipe and the image of the pipe are two distinct things. And that's also true in our images of the sky. So what you're looking at is an image of a galaxy cluster. So each of these bright yellow blobs, those are galaxies in the galaxy cluster. But if you look really closely, you'll see that there's also these circular looking arcs. So these circular looking arcs are not galaxies in the galaxy cluster. They're actually galaxies behind the galaxy cluster. And because the galaxy cluster is so massive, it's changed the shape of the galaxies so much that they just appear as tangential arcs, circular arcs. So this is showing you directly in the data how the presence of matter changes the shapes of what we see and how we care about understanding these distortions themselves. They're a new form of information we're detecting. So now we can talk specifically about what the Dark Energy Survey measures. As I've said, we care about doing statistical measurements of structure in the universe from images of galaxies. Well, that's what we can see. We can see the galaxies. We can't see the dark matter. But we want to understand what the distribution of the dark matter is. So how do we do that? So in this diagram at the top, you see a square. In that square, there's a distribution of dark matter. It's this web that it's formed. We don't know what that is in real life. That is done in a computer simulation, okay? So we've simulated what the distribution of dark matter is and how it has evolved. On top of that web is a web of galaxies. The web of galaxies largely traces the web of dark matter, and we can see the galaxies. So one of the ways we can understand the distribution of dark matter is to just understand the distribution of the galaxies. That's point number one here, galaxy clustering on the left. We can measure how clustered galaxies are. The quantitative way of saying that is, how likely are you to find a pair of galaxies separated by a particular angle as a function of that angle, small angle, large angle? That is a quantitative statement, that likelihood. And that tells you exactly how clumpy the galaxies are, which is related to how clumpy the dark matter is. So that's the first way we can understand the underlying distribution of dark matter that we can't see directly. The other way depends not on the positions of the galaxies, but on the shapes of the galaxies. So that's number two, called cosmic shear. Now, instead of looking at how likely we are to find a pair of galaxies separated by a particular distance, we're saying how related are the shapes of galaxies separated by a particular distance? How likely are they to be related? This is telling you also about the distribution of dark matter, because as I've said, the shapes of those galaxies are sheared, they're altered by the dark matter that they had to pass through to get to us. So we can use not just the positions, but also the shapes to understand the distribution of dark matter, cosmic shear. The third is just a combination of position information with shape information. Here you look at the correlation, how the relationship between the shapes of distant background galaxies and the positions of nearby foreground galaxies. It combines the information. So these are three different kinds of measurements we can make, all with the same data, and we combine them. This is a statistical advance in some sense, that we're combining data from the same underlying truth, but different kinds of data in order to maximize how much information we extract from the data. So that's the kind of measurement we want to make, but unfortunately it's extremely challenging. And I want to talk in detail about what these challenges are, of which there are many. Here's a cartoon to help us understand that. So we're going to talk about all the things that happen to the image of a galaxy. Let's start from the upper left. Here you have a cartoon of this sheep. And this is what it looks like. But as I've said, that image is going to be sheared. It's going to be distorted due to gravitational lensing. So that moves us one panel to the right. Its shape has been changed. That's not the only thing that's happened, though. The light has also had to pass through the Earth's atmosphere. And the Earth's atmosphere is turbulent, as anyone who's been in an airplane knows. That turbulence also bends the shape of the light. So that's something we call the point spread function, or PSF, as it's shown here. And that's also going to change the image. That's not it. Then once the light's passed through the atmosphere and gone through the telescope, hit the mirrors and whatnot, then it hits an actual camera, which is has individual pixels. So the image we see is actually pixelized because we have no other choice. The process of converting those light particles to electrical signals that we can then interpret with computers, that's a noisy process. It's not a perfect one-to-one correlation. So there's an additional noise and uncertainty that'll be introduced by that process. So that's going to further change our image. And then finally, we've only considered a case where there's one individual thing we're looking at. But in reality, galaxies, the images, they can be overlapping. They can be blended because one galaxy, one galaxy behind another galaxy, they can be overlapping, largely overlapping. And we don't want to throw away all those data. So we also want to understand what happens when we have galaxies images that are blended. This just gives you some idea of an account for just how many effects there are that we need to account for. Each of these issues is dealt with by whole teams of scientists. So with that, I'm going to talk a little bit more about something that I work on very directly. We've talked about gravitational lensing, which is very analogous to lensing you'd see with a magnifying glass or any kind of anything that bends light, water even. Here, let's think about how lensing depends on distance. So there are 4 images here which represent 4 different moments in time. And there's a piece of paper shown, graph paper, where there's a straight grid, a square grid drawn on that piece of paper. And what you're looking at is you're looking through a wine glass. At the base of the wine glass, there, the stem. At the base of that wine glass, the glass itself is going to bend light. And as you pull that wine glass away from the paper and then put it back down, you see that the amount of bending it does changes. So the amount of distortion we see, it doesn't just depend on the fact that there's a wine glass there. It also depends on where that wine glass is, where the lens is relative to the source and the observer. This means that if we want to interpret the change in the shapes of galaxies due to gravitational lensing, we also need to understand, to some extent, the distances between us and the lens matter and us and the distant galaxies. This turns out to be really challenging. So this is, in some sense, the elephant in the room. It's that if we want to interpret these shear measurements of the galaxy shapes, we also need to have some constraints on what the distances to the galaxies are. So what would that look like to know that? That would look like a plot like this. This is an illustration of what the data would look like. On the horizontal axis, it represents galaxy distance. So things that are closer to the left-hand side would be galaxies that are closer to us. Things on the right-hand side would be galaxies that are further away. And the vertical axis, the y-axis, would represent how many galaxies have that particular distance. So there's a curve here which represents how many galaxies do you have at a particular distance as a function of that distance. This is the diagram we want to draw, because if we can draw this, then we can interpret our shear measurements, how the galaxy shapes have been altered. But how do we do that? Think about this. If you just take a picture of something, how do you know how big it is if you don't know intrinsically how large something is? It's a challenging thing. And we rely on this principle that I've come up with at the mnemonic for, which is that objects in mirror are bluer than they appear. So we can understand galaxy distance, in fact, by understanding the galaxy color. Let's talk about why that is. So in the top diagram, you see a wave of light. That wave is, let's call this blue light, okay? And there also is represented the length of the universe at a particular time when that light is emitted. But as I've said, the universe is expanding. So because the universe is expanding, the space itself is expanding, the wave that is also going to get stretched out. And when that wave is stretched out, that's changing the wavelength of the light. So the wavelength, the distance between each peak here, that's getting larger. And that means that the light is actually going to be redder. This is a key principle that we can rely on. Galaxies appear redder than they really are. So they're bluer than they appear. And we want to measure how much redder galaxies appear in order to have, that's our proxy for distance. It's what we're going to treat as our distance. It works for our experiment. So that's the measurement context. This is the kind of measurement we want to do. We want to measure galaxy shapes, positions, and we want to use their colors to better understand the distances. With that, we can dive in to the state of the art. All right, so we talked about the elephant in the room, just measuring galaxy distances. I wanted to spend some time talking about this because this is what I do in particular. And this is the first time we'll be seeing plots of how scientists look at data. I wanted to spend some time talking about how scientists, what scientists look at when we're looking at data, to give you a sense for how we think about interpreting data and how we communicate with each other. We've tried to simplify these diagrams to make them more accessible as well. So with that, there's a quote here, grown-ups love figures, and it is very true. So here on the horizontal axis, instead of galaxy distance, we have galaxy redshift, because I told you how much redder it appears, that's in some sense a measure of its distance. And on the y-axis, again, we have number of galaxies. And I'm showing the measurements we did for the dark energy survey. Each of those symbols represents a group of galaxies. How does that work? Where the symbol is on the horizontal axis, how far it is from left to right, that tells you how far away is that group of galaxies. So that's one thing. Where is it on the horizontal axis? The other thing is, where is it on the vertical axis? That means how many galaxies are in that group of galaxies. So things that are further up, there are more galaxies in those groups. And then there's one more thing. I could have just drawn points here to represent those groups of galaxies, but I didn't. Instead, what we have here are symbols. And the symbols, they tell you that we don't actually know exactly what the truth is. Instead, we can tell you the truth is about this plus or minus this. And these symbols, where it's wider is where we think it's more likely to be for every particular group of galaxies. And where it's narrower, that's where it's less likely to be for any particular group of galaxies. So this is our measurement of the distribution of galaxy redshifts, which is our proxy for galaxy distance. With that, we can see the essential that's visible to the eye. We can interpret our shear measurements and get a map for dark matter in the universe. Here's what that map looks like. So again, you're seeing the whole sky, which is a sphere, and it's just distorted in a way so that makes it look like an oval. And the shape with all the purplish color, that is the dark energy survey map of dark matter in the sky. The darker points are where there's less dark matter. The lighter points are where there's more dark matter. You'll see again that we're avoiding the plane of the Milky Way because that has all the dust and stars. It's just going to interfere with us measuring really faint, distant galaxies. So now let's talk about another measurement, galaxy clustering. Remember how I described this? This was how likely are you to find a pair of galaxies separated by a particular distance as a function of that distance? Let's break that down. This is what that looks like to the scientists. So here, the horizontal axis, that tells you what's the angle between galaxy pairs. So if it's further on the left, that angle between galaxy pairs is small. You're looking at galaxies that are really close together. On the right, you're looking at galaxies that are really far apart. And on the y-axis, the vertical axis of the top panel, it says, how likely are you to find a pair of galaxies separated by that distance? So don't worry about the numbers, but higher means more likely, lower means less likely. And the data, what we measured with 100 million galaxies, are the black points, the black circles with little tick marks above and below them. So that's what we measured. We measured exactly that, galaxy clustering. What's really interesting, what I want to point out about this, is that this relates directly to things like dark matter and dark energy. This is a quantitative way of showing it, however. So there are a couple other elements of the plot, and we, as scientists, we always look at every element of the plot. So in addition to the points, there's also a black line. What that black line is telling you is what is our best fit theory to those data. So we came up with a theory for the universe, which has a certain amount of dark matter, a certain kind of and amount of dark energy. And that theory tells you exactly how much clustering you should see. And you'll see that that theory or model matches the data quite well. So the black curve matches with the points. Now, what we've added to this plot, specifically for you as an audience, is what happens if we just added way more dark matter? And that's what's shown in the orangish curve. So if you put 20% more dark matter, then that changes what the galaxy clustering yield measure is. So you can see here, and it's a very subtle effect when you look at it like this, but this is just what the data are. Adding 20% more matter to the universe changes this measurement. So now you can see, yes, the measurement we've done, it tells you how much dark matter there is in the universe. The other curve, the purple, is if you had 20% less dark matter compared to our best estimate. The bottom panel is just showing the difference between the curves to make it a little bit more obvious. And since we're doing this exercise, there's one more feature in this plot, and there's a gray bar, like a gray rectangle on the left-hand side. That's because, as I said earlier in the talk, this story of telling you, this tug of war, it determines how the universe looks on large scales of distance and time. But once you get into small scales, so galaxies that are separated by small angles, other things start to matter. Things like exploding stars and exotic astrophysical things that can dump energy and blow like extreme winds into space, and that'll affect the clustering of galaxies. So all those small angles that are represented in the gray region, that's where we're saying, you know, all this other complicated astrophysics is just interfering too much with our ability. We can't simulate it. It's just interfering too much. So we're going to throw out those data. So the reason I point that out is to give you the sense that we have to be extremely careful about what data we use. You can see here a huge amount of the data we're actually throwing away because we can't be perfectly sure that we can simulate all those complicated astrophysical effects well enough. And that brings us to our end here. This is the big result. So this plot is showing on the horizontal axis what fraction of energy in the universe is matter. So remember I said earlier it was about 25 or 30% when you add up the ordinary matter and the dark matter. That's what's shown on the x-axis. You can see the number ranges from, on the left-hand side, 25% to on the right-hand side, over 42%. And the y-axis is how clumpy is the matter in the universe. We don't have to talk about quantitatively how we make a number for that question, but just trust that we make a number for that question. And as I've said, scientists can never tell you exactly, or experiments can never tell you exactly what the truth value is. We can only tell you where we believe it is with some uncertainty. So with that, I have a quote from The Catcher in the Rye. Holden Caulfield said, "People always think something's all true," and that's of course never the case. So we think from the dark energy survey that the true value of these two numbers together lies inside the gray, the blackish grayish region. We think the best estimate is really sort of toward the center there. That's what we think our best guess is. But all we can really say is that we are 68% sure that the truth is within the inner dark circle, and we're 95% sure that the truth is within the outer grayish region. So that's how we communicate our understanding of what the true value must be given our data. It's probabilistic. And what's really interesting here is to compare this, as I said we'd do, with observations of the oldest light in the universe, which is in the green. So that's similarly what their experiment of the oldest light in the universe, the cosmic microwave background, gives you. And these results are not inconsistent because the truth is in these large blobs, and there was an overlap between those large blobs. But it's interesting that they don't completely overlap in a sense. It's interesting that the late universe says the universe should be a little bit less clumpy, is less clumpy. This could just be a statistical fluke, but it turns out you can do many other measurements similar to what we've done, and they're all just show that the late universe experiments are just a little bit lower. And that doesn't mean they necessarily disagree, but it's a bit suspicious. It's suspicious in that it suggests maybe we aren't understanding everything that we're measuring perfectly well. Or maybe our model for the universe, the story we tell about how the universe is developed, is missing something. The fact that it seems to be showing some cracks under stress is something that's very interesting to us because it's been confirmed by multiple experiments. And this, of course, relates to dark energy because the clumpiness, as I said, is in part due to the nature of dark energy. So this is the state of the art. I wish I had an answer to give you, but we don't have that quite yet. We're hard at work trying to better understand what's going on here. So to end, our summary is then that our cosmological model is at once very successful and demanding of increased scrutiny. We're hard at work to work out the remaining mysteries. With that, I'm excited to start the question and answer session with Dr. Ami Choi and Dr. Spencer Everett, two other collaborators in the Dark Energy Survey who are experts in how we do these measurements. Looking forward to your questions. Thank you.
Okay, well, Justin, thank you very much. Very beautiful talk. These slides are gorgeous.
Thank you.
We'll now open the discussion for questions. I remind you again, many people have written questions into the question and answer box, but if you have more questions, please just type them in. We'll see how many we have time for. And maybe you should go ahead and introduce the panelists.
Great, yeah, so everyone should be able to see Ami Choi, Dr. Ami Choi and Dr. Spencer Everett soon. They're both scientists working in the Dark Energy Survey at California Institute of Technology, Caltech.
Hello, can you hear us?
Yeah, we can hear you.
Can we change it to the gallery view so we can see everybody? Well, while we're trying to do that, let me shoot you folks some questions. First, some more practical ones. Martha was very interested in the picture of you, Justin, at the beginning, sitting at a desk with a lot of computer terminals in front of you. That was taken at Stanford, and the telescope was in Chile. So how does that work?
Yeah, in this case, the telescope was in Arizona. And yes, this picture is taken at Stanford. Excuse me. We can downlink the data over the internet essentially. So this was done over Zoom. We have a special observing room which has some things that help us for this kind of thing where we have an extra power supply. So if the power went out, we'd still have power in our room for our computers and have a more reliable internet connection. But yes, we're interacting with people who are on the mountain itself, who are operating the telescope. And the scientists tend to operate the instruments, the cameras that are collecting the data. So here, the interface with these screens, we're operating the instruments, the camera, the fiber optic cables that are collecting light, and the people on the mountain are operating the telescope itself. Sometimes we're lucky enough to be able to go to the mountains. Over the past year, that's been more difficult, of course.
The schedule for which way the telescope is going to point has to be worked out well in advance?
Yes, so it should be, but of course, things always change. So we do have to think on our feet all the time to adjust to the fact that if clouds are covering the sky and you miss, delays you, what do you then do with your schedule? It's not a perfectly solvable problem. You have to make concessions depending on things that you can't control, like the weather and instruments not working properly. So you're always thinking on your feet, which can get more challenging as the night goes on.
One thing I'll add there is that, as Justin was saying, it's incredibly important to figure this out quickly because telescope time is very expensive. So you need to have this sorted out and be able to adapt to the situation. And one of the ways we handled this in the Dark Energy Survey was actually a lot of people spent many years working out algorithms that would take in all of this live data as we were going. So we would start the night saying, I want to look in this part of the sky because we're missing data there. And it's going to be high up in the sky with less atmosphere, but then there's a cloud there. And it will automatically adjust to the situation and decide to point somewhere else where the conditions are better. Now, and sometimes when you're observing, you don't have the luxury of something that nice and you have to do more of this mental processing on your own. But we also spend a lot of time trying to automate these processes for when you have to do it quickly.
Okay. There's also a question about the camera. You said you need special chips for the camera, which are thick. What's the process for that? Are these off-the-shelf things, or you have to actually order these chips to be manufactured?
Yeah, in the case for our kinds of experiments, these are special ordered, specially designed for our experiments. I'm not an expert on this. My understanding is that these chips, which can be made of silicon, are grown as crystals, and we have to then understand, because these are special made, we have to understand very well how they respond to light. So, for example, one of the things that affected the dark energy survey camera is because these crystals are grown over time and the humidity conditions in the room in which they're grown can change. There can be slight aberrations, slight changes in the silicon itself, and that'll affect how sensitive it is to light. These are things that are really in many ways inevitable, but we just have to understand them really well to essentially correct for them. I don't know if the other panelists have thoughts too.
I think you answered that really well. I know that they were made specifically at Lawrence Berkeley National Lab. So they were made by scientists, although some detectors made for telescopes are made by commercial companies as well.
Yeah, and in fact, one of the reasons DES got so much observing time for its survey is that we donated the camera to the telescope when we were done. And so the way we kind of bought our time was by developing a very nice state-of-the-art camera and getting to use half the time with it, and then they got to keep the rest.
Yes, maybe it's worth noting that SLAC is now mounting I believe, 2 gigapixel camera, a much larger camera, on another telescope, which is in Chile, which will take its first light next year in 2022. So that's called the Large Synoptic Survey Telescope, or actually now it's named after one of the discoverers of dark matter, Vera Rubin Observatory. And that's the next step. Edward had a very basic question. So how does the universe get a web of dark matter? He says dark matter should just move and clump up into one big universe lump because nothing affects dark matter except gravity. So how does the dark matter, A, get spread out all over the place, and B, form then into these lines and voids that you showed in the pictures?
Yeah, so I could start to answer that. I'm sure the other panelists will have things helpful to add. So dark matter is primarily affected, right, by gravity, which we know affects it. But keep in mind that the expansion of space is something, it's in some sense a gravitational effect as well. So dark matter does not, it does not overcome that, right? It is subject to that as well. So it's subject to that effect. And also we at this point know that dark matter interacts with other stuff only very weakly. We actually have not ruled out that it interacts with other stuff at all. And in fact, all the experiments we're running here on Earth really rely on the hope that it does interact with other stuff.
Yeah, so that's a really great question. And I think the intuition is basically right. If you look at a patch of the universe, there's a bunch of dark matter. What does it do? It collapses into blobs of dark matter. That's exactly what happens. But there is no, center of the universe that we know of. It's not just a little ball. It's collapsing into those balls all over the place from the early universe, where there happened to be just a little bit more mass just from randomness. And eventually the scale gets big enough that the gravitational attraction between those different clumps is much weaker than dark energy, as Justin was alluding to. So your intuition is right. It's just happening all over the universe. And then matter in between these things starts to fill the connections, which creates that web-like structure.
And the voids are formed by the dark matter moving out of one region toward other regions that attract it. So eventually you get this kind of pattern that you saw. Okay, Jerry has the following question. We know that in the local universe, there's something called the great attractor, where there's actually matter out there that's pulling local galaxies, I believe, toward us. And he wonders whether this could be the explanation of the overall stretching of the universe as an alternative to dark energy. Is it possible that there's some matter out there outside of our view that actually through its gravity is causing the universe to expand?
Interesting question. Just start to Spencer or Ami, do you have thoughts off immediately to answer that question?
Well, I think we're getting a lot of data from these big surveys and telescopes at many different, like looking back in the time and looking at larger and larger volumes of the universe. So my intuition here is that it would be pretty hard to have something like that really explain all of the observations that we see. I guess that people probably have also run simulations of this to see, you know, how would that impact observations that we can make, you know, like the ones that Justin was speaking about. But I think that we have a very wide range of observations going from galaxies that are local to us, and of course there we can't really see that far, so there might be something kind of hidden from view, but we also have observations for very distant locations in the universe, or rather, you know, looking back at the universe at early times. And I think it might be hard for that to be the explanation for the dark energy.
And in addition, so I'm guessing this is kind of where the question's coming from. We do know of a kind of a great attractor-like thing in the semi-local universe. It's a big blob of stuff that has a big gravitational pull that makes us maybe not in the most uniform area of matter density in the universe. But at least from what I had read, the effect of that, even if you're extremely generous and how strong that effect could be, was a fraction of what you would need to explain the dark energy measurements we see. So even extremely anomalous things like this have been insufficient to explain dark energy. So then you quickly have to design a very strange system to explain our effects versus something like dark energy, which is a single number in a theory that already can allow it. So it's far simpler to assume that something like dark energy exists. It requires much less strange oddities and construction.
Yeah, Stormy has another question which is relevant to this one. She'd like to know, you described the early universe, the universe of the cosmic microwave background, as being very smooth. So how do we know how smooth it is? How do we measure that? And also, if it's very smooth, where did the little unevenness that you talked about come from? So maybe you folks can address both of those questions. How do we know it was so smooth back then when the cosmic microwave background was emitted? And where did the little bumps on it come from?
Yeah, I mean, this is a really great question. And while I'm not an expert on this, I can say that, so the smoothness, it's hard to tell from the image I showed, because the image I showed was in many ways designed to illustrate what clumpiness was there. But the smoothness is evident when you just change the scale of what clumps you're looking for. So it was millionths of degrees was the units of the color changes. So if we had looked at thousandths of degrees or hundredths of degrees, 1% of a degree, it would look much more smooth. And we describe it as smooth. The original observations, of course, done in, I think, 1965, it was just a completely smooth map. And the big question was, what is this? As far as what is the origin of this, the root of the idea is in the randomness of quantum mechanics. So in the early universe, so quantum mechanics is really an inherently probabilistic theory. Events are determined inherently probabilistically. And that's happening in the early universe. The distance scale of those quantum mechanical rules is more relevant, right? So now the distance scale of that distance scale is very small, but when the universe itself is smaller, that distance scale has a different impact. So the inherent randomness of the laws of physics, and in particular quantum theory, is going to inevitably lead to some differences. And perhaps other panelists have better answers as well.
No, I think that's a great answer on both fronts. And just for added context, you showed the great picture of the CMB and these what look like huge fluctuations that, as you said, have been scaled that way. Just to give people an idea, I mean, it looks like this big mountainside, but if you actually looked at it like in person, it would be like the peaks and valleys are one part in like 10,000 or 100,000. It's very, very, very tiny changes. But if you have a very sensitive instrument and can capture those, I mean, we get so much of our cosmology just from those tiny fluctuations. The fact that we exist at all, right? It all comes from those.
Let me back up and ask another kind of more instrumental or practical question. You talked a lot about the distortions that come from the sky, the fact that we're here on Earth and light is coming to us through the atmosphere. Of course, that's not true for telescopes in space. And so Rod would like to know how you compare your telescope to that of the Hubble Space Telescope. I guess it's much bigger. Could you give us an idea of that? And is it possible for Hubble or some other future telescope that we put in space to do this kind of survey?
Yeah, so the big difference is that it's much bigger. It's hard to put large things in space. Now, of course, we're always improving. So future space telescopes will be bigger than past space telescopes. But that, as a general rule, that is a fair thing to, that's the general rule. It's hard to put big stuff in space.
Yeah, so Hubble, I think, is like a 2 point something diameter mirror in meters. And so the telescope that we're using for the results that Justin showed, that's like a 4-meter diameter mirror. But the main difference is that the camera is much, much bigger and heavier. And so I think the largest cameras that are flying on the Hubble Space Telescope are really a tiny fraction of what you can get in your field of view. So how much of the sky at once that you can see. I don't remember the exact numbers here, but a very small fraction. And then Justin mentioned there will be future space telescopes that will go up. So one of them is called the Roman Space Telescope, and that will hopefully launch later this decade. So in the mid-2020s is when it's supposed to launch. And that one, it has a similar size mirror as Hubble, but it has 100 times the field of view. So the camera is much, much bigger. So that experiment will also be used to measure like weak lensing and galaxy clustering, the kinds of observations that Justin was describing.
And since they got to answer the question first, I get to back up with some Googling. So yeah, so the main Hubble camera is, it's less than 30 times the size of the one in DES. And it's because we're on the ground, as they said, you can build it much bigger. And so we have over twice the collection area, twice the bucket size for the light. And that's all great. We can build these giant ones on the ground. Where of course, the huge drawback of our ground-based telescopes is we have to look through the atmosphere. And all the twinkling stars, the twinkling is a terrible thing for the astronomer. It's all the light getting distorted. And so it's always this trade-off between really big telescopes on the ground that have worse resolution of what's on the sky versus these kind of smaller instruments that can zone in and make really pretty pictures like Hubble, but can't cover the whole sky.
So Eric has the following question for you. Justin, you talked a lot about trying to infer things from the shapes of galaxies, but how do you know what the shape of a faraway galaxy should be? So it's distorted, but you don't know what the original shape was. Why isn't that faraway galaxy just shaped sort of elliptically instead of spherically, or disc-like instead of round? How do we know if it's being stretched by gravitational lensing or whether it was just that way in the first place?
Yeah, truly excellent question. I had the same question as the first-year graduate student. Ami is one of the world experts on this, so maybe I'll let Ami answer.
Sure. Yeah, it is a great question. So we don't know for a given galaxy what its original shape looked like, because galaxies we think can come in many different shapes and sizes. And so what we have to do here for weak gravitational lensing is do a statistical analysis. So what we're specifically trying to measure is the coherent distortions of galaxies. So really for any given galaxy, like any single galaxy, the gravitational lensing effect that is applied to it is really typically less than 1% of the actual ellipticity of that galaxy. So for that one galaxy, we can't really tell how much it was lensed, but by doing averages over, so as the case is for DES, over 100 million galaxies, then you can measure a statistical distortion, which is like coherent. So we specifically look at, for example, pairs of galaxies, and we try to measure whether those two galaxies seem to have a coherent distortion. So there's something that slightly changes their orientation to be slightly like in a particular way, as opposed to just completely random.
Yeah, that's a great question. You should be a weak lensing cosmologist. It's exactly what we worry about.
AC has picked up, I think you didn't mention it in this talk, the current problem of the Hubble constant, which is the rate of expansion of the universe. So there's been some news that there's a discrepancy between the Hubble constant measured by Planck and the Hubble constant measured more locally by type 1a supernovae. And he'd like to know, or she'd like to know, has this been resolved? And what are the implications if there actually is a discrepancy? And maybe I should also add, could that be related to the possible small discrepancy that you showed on your last slide?
Yeah, really great question. I'm happy to start with the answer for that. So this problem called the Hubble tension relates to measurements of how fast the universe is expanding locally compared to what it should be from early observations of the early universe if you roll the clock forward to today. And there's a discrepancy, if you measure it actually, that expansion rate is faster. And this discrepancy is more significant. It's more in tension with the early universe than the measurements we're showing today. However, it is important to consider them both. It's important to consider them both at the same time, because they could be telling a story, because less clustering from late universe measurements, also more faster expansion from late universe measurements. They could be telling us something about the nature of dark energy. But it is also possible that they are the result of these measurements being very hard to do and us not accounting for everything. So to answer the question, no, it's not at all resolved. It is one of the burning questions that really, I think, motivates a lot of us. And that problem is actually statistically more significant than our problem, and we hope we're searching for answers.
Okay, I think we have time for just a couple more questions. One of them, this may cover some things you've discussed before, but it's a very important question. Christian would like to know, I understand that dark matter interacts with regular matter through gravity. But does dark matter also interact with other forces, like electromagnetism, strong and weak force? And similarly, do we know what it's made of? And let me just add to Christian's question, are we getting insight into that from the Dark Energy Survey? Or these things are too weak to measure in the Dark Energy Survey?
Yeah, so top level, just to start, the top level is that we have many experiments which attempt to make direct measurements of dark matter, and those rely on it interacting, for example, with electromagnetism. If it interacts with electromagnetism, we know it only does so very little. That's what we know so far. But it still could interact with electromagnetism in some way. And that's what many ground-based experiments to detect what it is, to detect the particle, the principle they rely on. Now, about the nature of dark matter, there are other experiments within the dark energy survey which get closer to that. So for example, looking at particular individual kinds of dwarf galaxies can shed light on the nature of dark matter, because looking at the dynamics of the system itself can tell you more about the strengths of these kinds of interactions. I'm not an expert on that, so maybe other panelists have information on that.
Yeah, something I'll just add as another example of a place you can try to understand dark matter in the Dark Energy Survey is in galaxy clusters. There are these huge, most massive gravitationally bound things that we know of in the universe. And so there are really great studies that look at these extreme environments. And so as a previous question had asked, why doesn't dark matter just all come together and blob up? That's basically what it does. But if dark matter interacts with itself, the way it will blob together in the center is very different than if it doesn't interact, and it will just screen right through itself. And so it'll be more diffuse if it doesn't try to interact with itself like all of our particles do. But if it does, it becomes more cuspy. And so if you can make extremely precise measurements in cluster cores with our really nice camera, be really careful about deblending all the light that is around, really being able to detect subtle things, you can make constraints about whether this is more likely to be caused, this kind of cuspiness, from non-interacting dark matter, which is what we normally assume, or more interesting exotic things that do interact. That's just one example.
Okay, and the last question, it's from John. The way he asks it is the Dark Energy Survey a dedicated survey? Is it always taking data for the DES and nothing else? So I guess my interpretation of this question is all this data just dedicated to measuring these parameters that you've described, or are there other uses for it, maybe that other people in your collaboration are making use of?
Yeah, so there are definitely other uses for it. We can do things as nearby as solar system science, nearby detecting asteroids, for example. We can do all that with the data. I would say that the experiment was designed with a primary goal and with secondary goals. So what I talked about today is very close to, that's sort of the primary goal. Secondary goals are not entirely out of the designer's minds when they're designing the experiment, but they take less importance in determining how we're going to build the camera. What are the specifications we need to meet? So the answer is sort of in between. There's a primary goal and there's secondary goals, which matter as well. And then I'll also say that during the time of the survey was a limited amount of time. As Spencer said, it was a 6-year survey, and we got more telescope time because the camera has now been donated to the observatory. So the camera now no longer belongs to the Dark Energy Survey. The Dark Energy Survey will make all the DES data, all Dark Energy Survey data will be public on a certain schedule. And after that, the project will move into an archival mode where all astronomers can access the archival data and do hopefully very interesting science with the data set.
So this is going to be a public database, and anyone can go and look for their favorite asteroids, exoplanets, whatever they think could be found there.
Yep, that's the roadmap. There's just a schedule for, there's still continues to be analysis to be done, but there's a schedule for that, yeah.
Okay.
And so the thing that people are most interested in are probably the images, and the images are largely already public, and really stacked, processed, really nice ones for the first 3 years all put together are also public. The things that take longer are more like the science products, but if you just want to look at the sky with our data, that is already available.
Yeah, I just dropped a link in the chat, which is one of there's different ways to get to this data, but I think what I dropped in the chat is one of them where you might have to look around a bit, but there are links where you can actually go and make cutouts of the DES data and make pretty pictures and look at the galaxy images. So I think one hope is that as these data get released to the community, that other people, not just other astronomers at research institutions, but just the community more broadly can make use of these images and maybe discover new things and find new stuff in the data that we haven't thought about or haven't noticed before. So that's, we encourage everyone here on the call to go and look at it themselves.
Okay, well, look, this is a good place to stop. Ami, thank you very much. Spencer, thank you. Justin, thank you very much for this beautiful talk. The next SLAC public lecture will be the week before Thanksgiving in November. And if you're on our mailing list, you'll get a notice of it. If you're not on our mailing list, look us up at SLAC, send us an email, and we can put you there so you'll be notified of these in the future. And let me just say also, there'll be a brief survey when the meeting ends. So if you would take the survey, that'll help us serve you better. So looking forward to seeing all of you in November, where we're going to hear about a very different topic, the use of X-rays to understand photosynthesis. Just another thing that SLAC does. So we look forward to seeing you then. Thank you very much.